now we will give input as AM signal and we will see what will be the output at the of envelope detector. So, if we consider the sinusoidal waveform, single tone sinusoidal, then the AM signal will look like this with modulation index less than 1. Here we have also considered the modulation index less than 1. That is why the minimum envelope is in the positive side. We know this because we have seen the time domain waveform, and in the time domain waveform we know when the modulation index is less than 1, then what will be the AM signal. So, this is the AM signal, and suppose the capacitor is charged to the maximum value. This is charged to the maximum value. This is green line is the capacitor voltage, and after this the input is now AM signal and input is AM signal. So, now input is decreasing. So, input is decreasing and capacitor is charged to the maximum value. So, input is decreasing whenever the input is less than the capacitor voltage. We have seen in the sinusoidal case whenever the voltage across the diode, that is the input voltage of envelope detector, is less than the capacitor voltage, then diode is reverse biased. So, the input voltage is decreasing, capacitor voltage is more, so the diode is reverse biased, and when the diode is reverse biased, it starts decreasing. So, it starts discharges, and when the capacitor discharges across the resistance R, it is decreasing continuously and the input is decreasing, and when at this point when both the voltage are same, and after this particular instant the voltage at the input of this envelope detector is increasing. So, now the voltage is increasing, and when the voltage is increasing, that means the voltage across the P side is greater than N side, then the diode is forward biased, and when the diode is forward biased, the capacitor starts charging. So, it charges to the maximum value and the same process will repeat. This discharging, this is charging, this is discharging, charging, discharging, and the process repeats like this. So, during this period when the capacitor is discharging, diode is off, and during this process when the capacitor is charging, diode is on. This green line is capacitor voltage. This red line is envelope, this is envelope. Let us show here by blue line because the original AM and envelope is same now. Now, this blue line is actually envelope. So, during the positive half cycle of this input, the diode works and it is forward biased, and when it is forward biased, it is charging, and in the reverse bias, it is discharging. So, to follow this envelope, this is actual envelope, and to follow this capacitor voltage, to follow the envelope of this AM signal, the capacitor voltage will be having some time constant, or the circuit is having some time constant. So, for proper envelope detection, to follow the envelope, the capacitor voltage, the time constant value should be very greater than 1 upon Fc and very less than 1 upon Fm. This is the condition when the capacitor voltage follows the envelope. When this condition is satisfied, then only the capacitor voltage follows the envelope of input signal. So, the envelope of input signal, which is drawn here by the dotted lines, these dotted lines, and this green line, which is the capacitor voltage, this capacitor voltage will follow this envelope very closely when this condition of time constant is satisfied. So, what will happen when this condition will not satisfy, that we will discuss here. So, case 1, when RC is less than 1 upon Fc. Suppose this time constant RC, this is the time constant RC, when this time constant RC is less than 1 upon Fc, it means it is discharging very fastly. Time constant less, it means the time is very less and it takes very less time to discharge completely. So, the 1 upon Fc is the time period of carrier signal. So, it takes very less time, even less than the time period of carrier signal to discharge completely. So, here I will show this. So, this is 0 suppose, and this is Tc, suppose this is the carrier time period, and before the carrier time period this capacitor voltage will discharge completely. So, it will discharge completely, before the time period of carrier. So, there is a big gap between this capacitor voltage and envelope. So, this envelope will not be followed by this capacitor voltage because there is a big gap now. Previously, when we maintain this time constant, this capacitor voltage is very closely following the envelope of the input signal. But now, when the time period is greater than the time constant, or you can say when the time constant is less than the time period of this carrier, this capacitor voltage discharges very fastly and it does not follow the envelope of input signal. So, this will happen when, let us draw another diagram for this. We know that the diode will not work in the negative half cycle, that is why I am not drawing the negative half of this AM, this negative portion. This is discharging very fastly. This will happen when RC is too small, when RC is too small. This is the case, and this will be the capacitor voltage. So, there is a big gap between these two. Originally, it should be like this. It should follow like this, but this red line shows that RC is too small. This shows that RC is too small. When the RC is too small, capacitor discharges very fastly. Capacitor discharges very fastly. Capacitor discharges very fastly even before the time period of carrier, and it does not follow the envelope properly, and capacitor voltage does not follow the envelope. This is the case 1. Now, case 2, what will happen if the RC is greater than 1 upon Fm? So, we have understood that if the RC is less than 1 upon Fc, then what will happen? It does not follow the envelope. So, for this we have to keep this RC greater than 1 upon Fc. Now, what will happen if we increase the value of RC beyond 1 upon Fm. So, if RC is greater than 1 upon Fm. 1 upon Fm means you can say the time period of this input signal. So, we can draw the figure for this also separately. If this is the envelope, now the RC is very high. RC is high even than 1 upon Fm. RC is high means RC is large means RC is suppose 5 seconds, it means that it is taking too much time for discharging the capacitor. So, the capacitor takes high time or big time for a long time for discharging completely. So, if the capacitor is suppose charge here up to here, suppose I am just showing it here. Now, from this point I am telling you that if the RC is very high, it means that the capacitor is taking too much time for discharging. So, it is taking too much time for discharging, that means it is slowly discharging. It is slowly discharging, it is discharging in such a way that it is not even following the envelope, it is missing this peak value, it is completely missing this peak values. So, it will happen when the RC is too large. When RC is too large, this is the case, when RC is too large, the capacitor discharges very slowly. That your capacitor voltage again does not follow the envelope. And this effect is known as diagonal clipping. Diagonal clipping. This effect, when the time constant is greater than 1 upon Fm, is called diagonal clipping, because it is missing this diagonal values of input, or it is missing the diagonal values of envelope. That is why this effect is known as diagonal clipping. So, to avoid diagonal clipping, if somebody will ask you, then to avoid diagonal clipping what should be the condition? So, to avoid diagonal clipping, we have to keep this RC less than 1 upon Fm. If this condition is satisfied, then there will be no diagonal clipping. So, there are two cases when RC is too small, that is even less than 1 upon Fc, it is not able to follow the envelope, and if the RC is greater than 1 upon Fm, then also it is not able to follow the diagonal value of envelope, and this case is called diagonal clipping. So, there are two conditions, according to that we can calculate the value of time constant. Now, the case 3 is, so far we consider the modulation index less than 1. Now, if the modulation index is greater than 1 and maintaining the time constant value between 1 upon Fc to 1 upon Fm, then what will happen? This is the over modulated case, and in case of over modulation, the AM waveform we have seen, there is a phase reversal in zero crossing here. And now how this envelope detector will work? So we are maintaining the time constant between 1 upon Fc to 1 upon Fm. So it is charging, discharging, charging, discharging, charging, discharging, and this process continues. And we get this green signal as output, capacitor voltage. This green signal, because we are maintaining the time constant between 1 upon Fc to 1 upon Fm, that is why it is closely following the envelope. But if we talk about the envelope of this signal, because the diode works only in the positive half cycle, so we will get only this positive half portion, and after passing through the smoothing filter, we will get the output in this way, because this will be the envelope here, because by connecting the positive peaks we get the envelope. So we are connecting the positive peaks, so these are the positive peaks, these are the positive peaks, and we are getting this positive peaks. After adding this positive peaks, we are getting the signal like this. So this is the output of envelope detector, but we know that the message signal is nothing but sinusoidal waveform. The input which was given to the input of amplitude modulator at the transmitter side was single tone sinusoidal, and for single tone sinusoidal we get the AM waveform like this when the modulation index is less than 1, either this or this. But when the single tone modulation happens and the modulation index is greater than 1, then that is over modulated, and when it is over modulated, the negative peak envelope, the negative peak envelope, the minimum peak envelope goes into the negative side. So it goes into the negative side, and the diode does not work here, but there is some portion in which we have the positive value, and because of this positive value the diode works, and diode works in this portion, but we do not get our original message signal. So in this case we will get some output, but that will not be our message signal. So now we can conclude that, now we can say, if we give input to the envelope detector sine wave or cosine wave, we get the output DC signal, and when we apply the input as AM wave, we get the output signal as message signal in certain condition. Suppose in the form of table I write, I am giving input sin omega naught t or cos omega naught t. This is input and this is output of envelope detector. Output of envelope detector. So in this case we get DC signal or constant. If we give AM signal, that is AC 1 plus KAMT cos omega CT with modulation index less than 1, then at the output we get message signal. We get the output proportional to message signal. But when modulation index is greater than 1 and input is AC 1 plus KAMT cos omega CT, that is over modulated signal, So when the signal is over modulated, it does not mean that we will not get any output. We will get the output, but that output is not equal to our message signal, and that is equal to the whatever will be the envelope of that input. So what is the envelope of this input? Envelope is AC 1 plus K into MT. and magnitude. Why we took magnitude? Because the diode works only in the positive part of the input signal, so that's why we will get the positive value only. That's why we have written magnitude here. So whatever will be the output, we will take the magnitude of it and we get the output. And in these two conditions we are considering that, even in all the conditions we are considering that we are maintaining this particular condition of time constant. So we are maintaining this particular condition of time constant. We are not getting the output in over modulation case, we are getting the output when the modulation index is less than 1. It means that we will say this envelope detector will work properly when the modulation index is less than or equal to 1. We can make the modulation index equal to 1 also, then also we will get the original signal back, because our our minimum envelope will not exceed the 0. So in case of over modulation, it exceeds the 0 and it goes into the negative side, that's why the information lies in that portion will be lost. But in case of modulation index equal to 1, the peak envelope and the minimum peak envelope, minimum envelope E minimum will be there and we will get the information. That's why we will make this modulation index equal to 1 also. That will be give maximum efficiency. Now we can derive one more condition when we consider the single tone sinusoidal modulating signal and AM signal for the single tone sinusoidal. Then what is the condition for modulation index, or what is the condition for the time constant RC? That can also be derived with the same condition, that the capacitor voltage should follow the envelope of input. So next we will see the condition for a time constant for a single tone modulating signal. So for a single tone modulating signal, expression of AM is given by S of t, let us say AC 1 plus MA cos omega mt cos omega ct. The envelope is denoted by envelope. This is the envelope. What is the envelope of this particular AM signal? So envelope is AC 1 plus MA into cos omega mt. So what is the condition of time constant? So to follow the envelope properly, the slope of capacitor voltage should be greater than or equal to the slope of input signal, that is AM signal. So we will consider slope of capacitor voltage VCT should be greater than equal to slope of envelope. Slope of envelope, because envelope should be followed. So envelope, in the envelope our message signal lies, so that's why the capacitor should follow that envelope. So we have to make this condition properly, then only we will get the message signal back. So we are making this condition, and according to this slope, how we can calculate the slope, or you can also write the magnitude of slope, and magnitude you can also write. Actually the condition is for the magnitude of slope of capacitor voltage, because everything will be positive, because the diode will work in the positive side only. So that's why magnitude of slope of capacitor voltage should be greater than equal to magnitude of slope of envelope. So how do we calculate the slope? So to calculate slope, we will be differentiating dVCT upon dt, and this should be greater than equal to slope of envelope, and envelope is denoted by E here, so dE by dt and its magnitude. So what is the capacitor voltage? So you know that whenever there is a RC circuit, the capacitor is maximum at t equal to 0, and as the time is increasing, the capacitor voltage will be exponentially decreasing. So the capacitor voltage, from the network concept, we know that it is charged up to the maximum value, that is the envelope, and then it starts discharging with the time constant RC. so e to the power minus t by RC. So exponentially it decays. So when we actually discharges the capacitor, the waveform you draw, it should be exponentially decaying, but because the difference between the successive pulse or the difference between the successive carrier is very less, that's why we can approximate it to the linear equation. So this exponential term will be approximated to linear expansion, that is 1 minus t by RC. Because when you expand this exponential, you will get, we know this formula, right? So e to the power x is written as 1 plus x divided by factorial 1 divided by x plus x square by factorial 2 and so on. So this nonlinear term is eliminated because the difference or the time period is very less in case of carrier, because the carrier is a very high frequency. So the time period is very less, and that particular small portion, in that particular small portion we see only the linear portion of that exponential decay. So we consider only the linear term. Now if I differentiate it to get the slope of this capacitor voltage dVct by dt, we get minus E upon RC, and because we have to consider only the magnitude, dVct upon dt, magnitude is E upon RC. So this is the first condition, that means the left hand side of our condition. Now we have to derive this dE by dt. So what is the dE by dt? So the envelope is AC 1 plus MA cos omega mt. Now dE by dt will be minus AC MA omega m sin omega mt, and if I consider magnitude only, dE by dt magnitude is AC MA into omega m and sin omega mt. Not the maximum value, I am taking just magnitude of it. So magnitude will be when we consider the positive sign only. Sin omega mt maximum value if I consider, then it is AC MA omega m, but we do not have to consider the maximum value, we just need to calculate magnitude of it. So that is why we get this result. Now if we put this condition in this particular equation, then we will get E upon RC is greater than equal to AC MA omega m sin omega mt, or we can also write 1 upon RC greater than equal to AC MA omega m sin omega mt divided by envelope. Envelope is AC 1 plus MA cos omega mt. This AC and AC will get cancelled, and we get 1 upon RC should be greater than equal to MA omega m sin omega mt divided by 1 plus MA cos omega mt. So there is some value of right hand side which is maximum because or minimum, because 1 upon RC should be greater than equal to this value. So there will be some minimum value of this right hand side, and above this the time constant is to be considered. So 1 upon RC should be having some minimum value. Let us say this value is suppose 5. So this ratio if coming 5, that means 1 upon RC should be always greater than equal to 5. So this right hand side should be having some maximum or minimum value, and above which the RC is to be considered. So to calculate the maximum value of this right hand side, we will differentiate it and equate it to 0. So when we differentiate it, 1 plus MA cos omega mt whole square, this is 1 plus MA cos omega mt, and differentiation of this is MA omega m square cos omega mt minus MA omega m sin omega mt and differentiation of this denominator, which is ma square omega square, and the differentiation of cos is minus sin, so sin square omega mt, and this should be equal to 0. So, to calculate this maximum value of this right hand side, because the whatever will be the maximum value above which there should be a value of 1 upon RC. So, to calculate this maximum value, we will differentiate and equate it to 0. So, when we solve this, we will get some condition. This is 1 plus or ma omega m square cos omega mt plus ma square omega m square cos square omega mt plus ma square omega m square sin square omega mt equal to 0. So, now we get omega m square common in all. So, it will be cancelled, and here the sin square and cos square will be 1. So, we are getting ma cos omega mt plus ma square, and this is equal to 0. So, ma equal to minus of cos omega m t, or you can also write cos omega mt is equal to minus ma, because ma square here will be and 1 ma will be cancelled. So, cos omega mt is minus m square minus ma. So, what will be the value of sin omega mt? So, sin omega mt can be written as 1 minus cos square omega mt, and cos square omega mt means 1 minus ma square. So, because we have to calculate the maximum value of this right hand side, so we need to calculate this sin omega mt and cos omega mt. So, the value of this cos omega mt is minus ma and sin omega mt is root over 1 minus ma square. So, if we substitute these values in this equation, we will get the value of RC, that is 1 upon RC should be greater than equal to ma into omega m root over 1 minus ma square divided by 1 plus ma, and cos omega mt is minus ma. So, we get 1 minus ma square, or after solving this you will get RC less than equal to root over 1 minus ma square divided by ma into omega m. This is the value of time constant for single tone modulating signal. If it is given that the single tone modulating signal and the AM signal, so for this RC, the condition of RC you can calculate using this formula also. So, we have two formulas in case of envelope detector. One is the formula for RC, RC should be greater than 1 upon FC and less than 1 upon FM, and the second formula is RC less than equal to root over 1 minus ma square upon ma into omega m. And third, the important point in envelope detector that you should remember is it works properly when ma, that is modulation index, is less than 1, less than equal to 1. And the fourth condition you should remember, to avoid diagonal clipping, the time constant RC should be less than 1 upon message signal frequency. If it is multi-tone, then it should be less than 1 upon maximum frequency component present in message signal. So, this is all about the envelope detector, and we will solve few questions basis on this envelope detector also.